Hi, I'm Bill Caden. I'm a faculty member in the Department of Physics, and as you'll probably see, I'm quite interested in finding new members to work in the research group. Before I get started, I'd like to thank Professor Al-Rawi and the remainder of the Undergraduate Life Committee for organizing this event like usual. I'd like to thank all of the undergraduate students who have made the time to attend and see what's out there and maybe get involved in some research. Um, our group specializes in two things predominantly, and we'll jump right into it. Those things are thin film epitaxy, that provides an approach by which we can controllably grow single crystalline films with fixed terminations and vary those terminations, which is a key knob that we use in studying different materials. And then the way we study those materials is using what I'm terming UHV style in quotation marks. You'll see at the end why I put that in quotation marks. UHV means ultra high vacuum. Surface science approaches to materials and physical chemistry characterizations. So at the end of the day, what we're trying to do is use thing A, approach to materials synthesis, that allows us to make very well-defined materials with very homogeneous, atomically planar, well understood surface structure that we can then deliberately tune at an atomic level to explore what that tuning does to the properties that we're interested in a given study. And I'll give you a flavor of a few different areas where we've been doing research using that general approach. The first area comes out of a collaboration we've had going on and continue to have going on with Dr. Kevin Coffey in the Materials Science and Engineering Department. And in that case, what we're doing is we're using a lot of the clean room facilities in engineering to grow, to leverage epitaxy to grow ruthenium thin films at wafer scale on C-axis sapphire. That's a specific termination of hexagonal alumina. And one of the techniques that we tend to use to characterize these things is low energy electron diffraction, and that's what's going on over here. Now, that's very similar to something you would have seen in physics 2 and beyond that when you got introduced to double slit interference, for example. Basically, the way this works is rather than electromagnetic radiation, you have electrons, which effectively have wavelengths. And anything with a wave, as you've learned, can diffract. If there's basically a spacing of things in a fixed pattern. In this case, rather than a double slit, the crystal termination of the surface itself is the slits. And instead of having a one-dimensional array of those slits, you have a two-dimensional array of unit cells, right, that are formed by the crystalline structure. So then the crystalline structure gives you a pattern that instead of a one-dimensional series of lines is a two-dimensional series of points. So the points here tell you about the structure you have. In this case, what it's telling us is that the ruthenium we made is definitely single crystalline and very well defined. It's very sharp spots, hexagonal symmetry. So one of the things we did there is we made a series of 4-point probe measurements for the thin films, which we can vary the thickness of grown on the sapphire, to get an idea for what's going on with the resistivity. And what we did is we varied what we did to the surface. So we would take the same sample and basically do all sorts of things to it. And what we found is we could basically get the resistivity to just jump up and down and up and down. But by monitoring what's the physical properties of the film, physical and chemical properties of the film at each step, what we were able to learn here is that there is a certain condition. Well, one, the first thing we were able to learn is that we could selectively tune the resistivity bounce up and down, and that basically came down to what we figured from our characterization. What we were changing was surface quality. And what that means then is basically we could turn the surface from a fully specular, meaning very reflective like a mirror, to a fully diffuse surface. And so when it's fully diffuse, the resistivity goes very high because you're basically losing electron flow due to the scattering of electrons. And when it's fully specular, the electrons keep their forward momentum, so you get minimal impact to resistivity. And so the reason we're interested in this is power consumption in CMOS technology basically is at the interconnects. And copper is rapidly becoming obsolete because we've reached length scales where this surface loss becomes very important. And so what we're interested in and still pursuing with this project is as we go to very, very small length scales that we're now able to achieve, this is done by electron milling, so 50 nanometer length by like a 15 nanometer width is something we can make here out of this single crystalline ruthenium. What we're interested in is, are there conditions then when we can get ballistic conduction over the length scale that we need so that we're basically not losing power in these interconnects? So this is an ongoing work. Something else that we are involved in is model catalysis is what we'll term it. So here what we're doing is we're trying to simplify the interfaces, which is where all the interesting chemistry happens in heterogeneous catalysts. And a particular model system that I'll talk about here is molybdenum nitride. There's a lot going on here, but the long story short of it is molybdenum nitrides, it turns out, appear to be quite active towards something called hydrodenitrogenation. So that's basically a way of removing nitrogen from crude oil feedstocks. It's important to oil industry. And the type or phase of the nitride, so there's a gamma phase and a delta phase, appears to be important based on previous research. But it's not very well understood because well-defined model systems haven't really been explored in the past. So that's something we were involved in, is then can we develop a model system that would allow us to basically take a series of probe reactants and then explore how they interact with the different nitrides as a function of the phase to try to better understand what about this structure would make it more or less active than this structure of the same, in principle, nitride. And so we have some results to show here. We've published some results. This just shows basically how we go about developing a thin film. And so here's kind of our target. We grew this on ruthenium, the same ruthenium actually as the other one, so 0001. And this was our target kind of film structure. So you got molybdenum in dark and nitrogen in blue. So this is a top-down view. This is a side view of what we were trying to make. And then the different things we characterize to tell if we make that thing or not. So we use X-ray photoelectron spectroscopy is a very useful tool that we use a lot. We use that to tell how much of a different element is present at the surface of something. We use that to tell what kind of chemical state are those things in. So for example, here you got molybdenum and nitrogen. Where these peaks show up exactly, meaning the little bit of shift left or right, gives you information about whether or not that thing is oxidized or reduced, chemically speaking. The amounts then tell you how much of each, and you can put both together, then get an idea of stoichiometrically what kind of compound do you have. In this case, it was the molybdenum nitrate MON we were trying to make. And then by looking at the intensities as a function of the time that we expose to the molybdenum flux, we get a pretty good idea that we were growing fairly linear, meaning the depth of the film was increasing linear with time, so we were probably wetting the surface versus making little balls of things. Another technique we use to get a better feel for that is called ion scattering spectroscopy. And I'm not sure, yeah, okay, there, I can put myself away here. That's down here. That is nice because it's atomically surface sensitive. What we use there is helium ions that don't really like being helium ions. So basically the only chance you have to detect them, you scatter them from the surface, is if they only had one collision. Because if they have more, if they go deeper than that on the surface, they just don't come back to the detector, they neutralize. Due to that atomic surface sensitivity, you can really get a pretty good idea for the way these things grow. So basically what we're doing is we're tracking the nitrogen and molybdenum, and we can kind of characterize the way the intensity of those peaks grow as a function of the molybdenum exposure, and we see a clear breakpoint. This breakpoint basically is when we saturate. We saturate when the entire surface is covered with at least one of those types of things, right? And then we stop getting more. And long story short, this is basically telling us that, again, like we thought over here, we wet a layer before we grow a subsequent layer. So it gives us a good idea for how this grows. This tells us about what is growing. And then finally we use the lead like we did before, where here, like we said before, this is what the ruthenium looks like, ruthenium 0001. And then when we cover this thing with some molybdenum, initially we lose the pattern because it's a completely amorphous overlayer. And then what we do is we heat that stuff up within a nitrogen environment, and we can crystallize. And what we see is that the pattern that we crystallize to is the same as the underlying support. That's the templating effect that we use with epitaxy. So that's pretty good evidence that we made the thing we wanted to make. Okay, moving on. One of the last things that we've done recently involves applications of planetary science. I'm going to try to go quickly here because I've already used 10 minutes. The moon has water on it. The blue here kind of gives you an indication of the distribution of that water. I don't think this is actually the correct image, but the dark blue still is roughly that. The purple in the middle is not that. So anyway, the moon happens to be composed largely of feldspars. They have kind of this general building block scheme where you have cations that support charge imbalances created when you substitute aluminum for silicon within a tetragonal framework of interconnecting metal sites where the oxygens bridge those connections. So one of the things we wanted to understand, we wanted to get a better idea for what causes some of the variation in the distribution of hydroxyls noted on the surface of the moon. And one of the mechanisms by which that is proposed to have occurred, among many, is that you get a constant bombardment of hydrogen ions from the sun. They implant in the surface. The surface is this oxide. They react then with the oxide to form OH groups. Those OH groups, under thermal conditions, can recombine to make water. And that's all pretty well known from surface science. But what wasn't known from surface science is the specific nature or strength of that OH group in this type of geology, meaning the site here that's of interest is the aluminum oxygen silicon site. Most of the surface science that had been done previously had been for one metal oxide at a time, like a silicon oxide, an aluminum oxide, etc. But trying to interpolate between those things is not the same as looking at that site itself. So one of the things we were able to make here is a mixed oxide where the blue here could be either silicon or aluminum, and we can kind of vary the ratio and compare and contrast the chemistry that we'd see from two otherwise structurally equivalent films that had this structure, again grown on ruthenium 0001. So we could get some characteristics of the film, just like we showed in the previous study, where we have a brown film that is just SiO2 in this structure. So you get a peak for silicon, a peak for oxygen, no peak for aluminum, and you get a hexagonal arrangement due to the hexagonal arrangement of the structure. And then you could make the same thing with the same type of structure for an aluminosilicate, where about half of the silicon atoms have been substituted. So you see a decrease of half the silicon, you see some aluminum, and you have about the same amount of oxygen, but there's some subtle differences. Now, long story short of this is, by comparison, what we could do is something called temperature programmed desorption, which uses a mass spectrometer to analyze gases as they leave a sample. So in this case, we would dose a sample with water at low temperature and then observe the water that came back. And that told us something, because we know some of that water would actually cleave and bind as OHs. We were able to learn something by comparison with other literature about the quantity and strength of those OH groups, which are shown here in red. I won't go into the details too much here, but basically through this type of an analysis, we were able to pretty well lock down pathways by which this occurs. So here's this recombinative desorption in red and the temperature. And furthermore, we could get out the energetics of this, which were such that for the duration of time that the moon is hot and the temperature that the moon reaches in daytime, this is happening pretty much all the time in these equatorial regions. And then, of course, as you get colder towards the poles, it drops off a bit. So basically you can be making water all the time, and as it's hot enough to diffuse, if it were, desorb and reabsorb, you can basically distill the water from the equator where it forms more towards the poles where it condenses more. All right. Final area. This is emerging. We have a new piece of equipment that we recently received an award to bring to UCF. Should be here any day now. It's called near ambient pressure X-ray photoelectron spectroscopy. So we do, like I said before, we do a lot of X-ray photoelectron spectroscopy. The beauty of this instrument is it allows us to take one of these surface science approaches that allows you to have kind of a very, very detailed understanding of what's going on an interface, but apply it outside of what's traditionally limited to ultra high vacuum conditions. That's like 10 to the negative 10 torr, and take it almost to ambient conditions. And that opens the door to many, many, many applications that are not amenable to the vacuum chamber. And so this is something that we're very excited about, and we're going to be doing a lot of experimental development work in our group with this piece of equipment to kind of apply the types of techniques we are used to in a whole bunch of new directions, and do some pioneering work in that field. And that will be coming very soon. All right, so wrap this thing up. A lot can happen in a year. This is what the group used to look like. And so people leave, right? So we've been fortunate that people have been successful and moved on. But that means right now we're fairly desperate for people. So if anyone is at all interested in anything that they've heard here, feel free to stop by my office. I'm in Research 1, room 161. Drop me an email, check out the website for more information, but I'd be very interested to hear from anyone that might have some interest in working with us. All right, thanks.